we can compare APs and GPs with functions. They've got a lot of similarities and each of them can help us with the other. So arithmetic sequences where we're adding a common difference every time can be modelled as linear functions. And geometric sequences where we're multiplying every time by some common ratio can be modelled as exponential functions. Now, when we're working with functions, we tend to look at a table of values to be able to spot the rule or come up with the equation for a function. And sometimes it's easy and sometimes it's more tricky. When we're working with APs and GPs, we tend to make our thinking like this. We're talking about the number of the term and what the term actually is. But if we set it out like this, you can really see the similarities, and what we've just learned here about APs and GPs can actually help us way back here with spotting a rule. Now, to give you an example of how two separate pieces of maths can now come together and help you. If I was looking at spotting the rule here, I'd say, well, these are going up by 1, these are going up by 5, so the y's are going up 5 times as fast. So multiplying x by 5 seems like it must be involved. So I go ahead and I multiply the x values by 5 to see what I get, and I notice that they're all just 1 too big. So when I'm looking at what the rule is for what I need to do with x to turn it into y, I know I need to multiply it by 5, and then I need to subtract 1. Now this one was fairly easy for me to spot, but sometimes it can be hard to see what to do, especially when you're just learning this. Now we've just come up with a completely separate formula for finding the nth term. We said that we take a and we add n minus 1 lots of d, where d is the common difference and a is the first term. Well, I can do better than this. Let's get rid of the a and put a 4 there. And let's get rid of the d and see that we're going up each time by 5s. Now, is this the same formula as that? They don't really look the same. Well, let's check. If I expand this out, I get 4 plus, I've got 5 lots of the n, and I've got 5 lots of the minus 1. So I have 4 plus 5n minus 5. Well, that's actually 5n minus 1. And this is 5x minus 1. Exactly the same thing. Here we're dealing with n's. I could have made that an x though. And it's the same. So if you've got this formula, a plus n minus 1d, to model an AP, you could use that same formula to actually find the rule in a linear function, which is now a handy skill. Similarly, over here, we've got a geometric progression or sequence here, and we've got an exponential function here. Now, these ones are notoriously tricky to spot the rule. Here we can see that we're doubling each time, but we're starting with a 6. To figure out the rule of these ones can be tough. But now we have a trick, something that we can use, or a skill, if you like. We know that we can do the first term, which in this case is 6, and then we can multiply it by the rate. Well, the rate, they're going up by 2s, so it's 2 to the power of, and we've got n minus 1. So similarly over here, we would have the same thing, 6 times 2 to the power of x minus 1. Now, can you get it simpler? Yes, you could. 6 is actually just 3 times 2, and if we multiply that by 2 to the power of minus 1, we've got 2 to the power of something times 2 to the power of something. We could actually add those together, couldn't we? Sorry, add together the indices. So what we're going to get is 3 lots of 2 to the power of, well, what's 1 plus x minus 1? It's just x. So coming up with the rule over here, you might have been able to figure out it's 3 lots of 2 to the power of whatever our number is at the top, but this is tricky to find, and using this can be a gateway that can take you straight there.